Goodness. Okay. All right, so yesterday we were talking about intermolecular forces, so I just want to do a quick review over that stuff that we were discussing, and then we do have a new intermolecular force we're going to work on today also. Okay, so let's start with this practice problem. If I mix KCl with HBr, will that combination, that mixture, form an ion dipole force? So hopefully you remember from yesterday that in order for those two things to form that force, one of these things has to be ionic and one has to be polar covalent. Okay, so is either one of these things ionic? Which one? Cool, and how'd you know?
Because the potassium has like positives and the Cl negatives.
Yes, awesome. That's a great explanation. So the metal here will have a positive charge and the non-metal will have a negative charge, right? So we know that this is ionic for sure. Okay, so maybe it could form an ion dipole force. We just have to decide if this is polar. So how do you decide it's polar? It's kind of a pain. It's a long process. You're supposed to draw the Lewis dot structure. So there's his Lewis dot structure. And from that, you should be able to tell that it has a linear shape, straight line. And hopefully you don't even have to draw the Lewis dot structure. Maybe you can just kind of tell that if it's only two atoms, they have to be just in a straight line, right? And so now I'm visualizing it like this. And I can see that this is lopsided, and that means it is polar. So that's basically what we need to do is figure out in our minds, is this thing lopsided? And if so, that will make it polar. And why is it polar? It means that we have a negative side and a positive side within this molecule because the electrons are being dragged over here to this lopsided area. So it makes the side negative and the side positive. So now, do you imagine that when this goes in water, it can break into positive and negative? And do you imagine that this negative ion could attract to the hydrogen, and the positive ion here could attract to the negative of Br minus? So these two attractions, those are ion dipole forces. So that's what we learned yesterday. And is that okay? Does that feel like it makes sense? So I'm going to give you two more problems, and I just want you to tell me if they are ion dipoles or not. Okay? Let's stick with HBr, but let's change this one. What do you think? It is. Pratish says it is. So we have an ionic compound again because we have that metal here, and then we have the polar compound. So it is going to form ion dipoles. How about that combination? KCl plus CO2. Lynn is saying it's not. How do you know, Lynn? What are you thinking? Excellent. CO2 is nonpolar. Now, how are we supposed to come to that conclusion? If you draw the Lewis dot structure, it looks like this. And I'm actually hoping that you're not having to truly draw it out in every situation. Sometimes we do. Sometimes if you draw so many of these things, you actually start to remember them. So it's unfortunate, but like I have this one memorized, and that's just gross, but it happened by accident, right? And you might be in that same situation. But the bottom line is, you got to get the Lewis dot structure, and then can you tell it's a linear shape? If it's a linear shape, it has this shape here. You see how that is not lopsided? So it's nonpolar, and that's not going to have an ion-dipole force. There's no positive and negative sides in this molecule to attract to the ions. So you can't have the force forming, right? Okay, so what we want to do is just do more of this kind of practice, but we're going to do it on Schoology. So if you could go with me on your Chromebook, and if you're at home, I want you to open up Schoology. So we're going to do a little coloring. It's been a minute. All right, so I am going to, intermolecular forces. I'm going to the in-class assignments, and it should be the first coloring activity that you see. Ion-dipole forces. Okay, so let me explain here. When you open it up, it looks maybe a little bit weird, so let me tell you what to do. Okay, so there's two grids here. If you scroll down the page, you'll see that second grid. We are not using that second grid at all today, okay? So just stick on the first grid. All I want you to do is color in the boxes that do form ion dipoles. And if you do it right, it'll reveal a shape, like literally a geometric shape. Okay, so you can pick any color you want. You might want to change the transparency here so that you can like see through what you're coloring. But you're going to color it for about 7 minutes. And then we'll see if you've got the right shape at that point. Right, give it a shot. Here's the name of the activity again if you're still looking for it. So if you get done with it, turn it in. I'm just checking to see whether we need one time. So we'll take about 2 more minutes and then we'll just look at what you have if you haven't finished at that point. Okay, so 2 more minutes. Lila, yours is perfect. Micaiah, yours is perfect. Remember, it's a shape. If you're not seeing a shape, you might be way off. All right, go ahead and turn in what you have. It's completely fine if you didn't finish it. But I'm just gonna hopefully be able to get some attendance for my people at home by turning this in, all right? If you're at home, you definitely want to turn this in. Okay, so let's take a look at what the answers are. Let me see. Micaiah, I looked at yours already, so I know yours is right, so I'm going to open that one. And you guys can hopefully see it here. It's a rectangle. It's a rectangle. Oh, very creative. I know. Hold your applause. I impressed myself. But look, I'm wondering why, let's see if I can make this bigger here. There we go. Why are we not coloring in this one, like the pH3 and the H2O? So I did see some people coloring that one in, so I'm just trying to understand. Why am I not coloring in this one? Anybody in here know? What do you think, Pratish? Huh? They're all nonmetals, right? And so in order to have one of these be ionic, you must have a metal or a polyatomic ion, but I stayed away from polyatomic ions on this whole grid. So I'm basically looking for metals. P is not a metal. Why is P not a metal? Look at its location on the table. Isn't it to the right of that black jagged line that you see? So if it's on the right side of the table, it's a nonmetal. Same thing with NH3. N is a nonmetal. So guys, if you have all nonmetals, like we have in this whole central area, There's no ionic compound. And you might look at Si and think, well, maybe that one's a metal. Actually, it's a metalloid, which is still not a metal. So you'd want to assume that that's not going to be ionic. Okay, so hopefully that makes sense to you. We're going to go back to the board here for a minute. I just can't remember. Did we get through all of this stuff with you guys? I got through, oh wait, this stuff that I'm showing you is not right. We didn't do this animation, did we? Yesterday, I don't think. Okay, so I need to do that with you guys. Okay, so let me go back to the board real quick before I do this animation, just to show you something. Okay, when we are talking about ion dipole forces, I'm going to illustrate this first one again here to help us see that force. So let's say that this breaks apart into K positive and Cl negative. And so that is floating around. I'm just going to focus on the K positive though, right? It would attract to, actually let me turn it like this. It would attract to the negative dipole of the polar compound because it's positive. Okay, this attractive force, you can kind of measure how strong it is. If the K positive gets closer to the HBr, it creates a shorter bond, which we know from the last chapter is stronger, right? Also, the charge will make a difference. So you see how this is positive 1? Well, if it was positive 2 or positive 3, it would make a difference. So let's take these two charges. Let's make this red side the HBr, so we'll make it negative, I don't know, we'll make it negative 2. Even though it's not really negative 2, it just has a negative dipole. This one here, we will make be the K positive. And so we're going to change it to positive 1. Okay, so the positive 1 is here, and the negative dipole of HBr is here. There is an attraction between them, right? There's a force right here that's measuring that attraction. It's like 19 or 20. Okay, let's make the K positive be positive 2 instead of positive 1. What happened to the force? It went from 19 to 40. Can you see that? It like doubled. So the higher the charge, the greater the force of attraction. Let me change this thing like way high. Let's make it positive 9. Look at the force of attraction now. These guys are attracted to each other with great force. So the higher the charge, the greater the attraction. Okay, so let's go back to the board. If I had magnesium floating around this HBr, magnesium would attract to this negative also. Which one has the greater attraction? Magnesium. Because magnesium is in the second column of the periodic table, it's +2. And potassium is in the first column of the periodic table, it's +1. The greater charge of +2 will result in greater attraction. I did not talk about that yesterday, did I? I did? Sweet. I got ahead. Okay, now let me reset it back to +1, or 2, I guess, and negative. Okay, now we're going to make these close together. So let me actually click and drag this. As they get closer together, what's happening to the force? It's increasing. Okay, so as they get closer, they have more attractive force. Now, that force is not changing like it did when I changed the charge though, right? So the distance here does not matter as much as the charge mattered. Okay, so let's now pretend that lithium is in the mix. Lithium is going to attract to the Br also. Because lithium is +1, it would attract very similarly to potassium. It's also +1. But this magnesium is +2, it's going to have a much greater attraction. Okay, now if I get to the point where these two are similar, I can still tell which one has the stronger force though. Do you see their sizes are different? This one's smaller. That will actually allow it to get closer to HBr, and then that is going to create a shorter, stronger force. Okay, but we only look at the sizes once we've identified that they have the same charge, because charge is going to be much more important in determining the strength of the force first. Okay, so I've got a sign. Let me show you again. We look at charges first. If you have a higher charge, it'll automatically make a stronger ion dipole force. Only if they have the same charge should you look at size. If one is big and one is small, the smaller one will create the stronger force. What I just described to you is called Coulomb's law. It's the idea that higher charges create stronger attractions and that smaller sizes allow for closer proximity, and that creates a stronger force also. Okay, so we need to be able to use that knowledge there. Did I get through all of the practice problems? Here, I just can't remember. Did we do this practice problem, Br minus or Cl negative? No. Okay, so this is where we're going to pick up. Okay, so if you are at home, hopefully you can see this. We want to know which one forms the stronger ion dipole forces, Br minus or Cl minus. So first of all, it's -1 and -1. If they have the same charge, I look at their size. Which one's smaller? Chlorine. So let me actually illustrate that for you. Here's my smaller chlorine. It's attracted to the positive dipole of this polar molecule because it's negative. Same thing's true with bromine, but it's bigger. So because it's bigger, this force will be longer and weaker. So Cl minus, Cl minus is going to have the stronger force. Pratish, did you say it? You did. I'll give you a ticket. Okay, so we actually already did that. We are ready to talk about the second type of force. Guys, when we were doing this chart, remember I said pH3 and H2O cannot form an ion dipole, but they do form some kind of force, and that force is called a dipole-dipole. Okay, so dipole-dipole is the new force we're going to learn about. What is a dipole-dipole force? It's a force that happens between two polar covalent molecules. Okay? Two polar covalent molecules form dipole-dipoles. I know you can imagine how this force works. If I've got a positive and a negative dipole and two separate molecules, it's just that the opposite poles attract. That's the force. Right? So here's some examples of dipole-dipoles. HCl is polar, and so is HBr. So they attract to each other. The positive of one molecule attracts to the negative of the other. Guys, they're going to ask you to draw these forces on the AP exam. When you draw them, can you use a dashed line, just like I did? Don't use a solid line. A solid line represents a covalent bond. So we must use a dashed line to represent this force. Okay, and if you were to draw a dashed line between the two H's, that'd be wrong. Why? Because both H's are positive, and they would not attract. And also, don't do it between two negatives. It's got to be between a positive and a negative. Here's another example. The negative of this molecule and the positive of this molecule is attached. These are two identical molecules, though, right? So it is possible to have an intermolecular force between two of the exact same molecules. They don't have to be different, like I've shown here. Okay, can you have a dipole-dipole between Bf3 and Hbr? So what is the first thing we have to figure out? Are both of these covalent? Yes, they're both non-metals, right? There's no metals here. Okay, then I got to figure out, are they polar or non-polar? Okay, so you already know HBr is polar. How am I going to figure out Bf3? What do I do first? Lewis dot structure. Guys, I'm going to try to help you with Lewis dot structures a little bit. If B is surrounded by three F's, That means he'll be surrounded by 3 lines, right? Is it possible for him to have a lone pair here? No. Do you know why? Look at where B is on the periodic table. Is it that column that's going to be satisfied with 6 electrons, not 8? So he's satisfied right here like this. And so without even like doing much work, I know that this B is only going to be surrounded by these 3 lines, and therefore its shape is trigonal planar. And now in your mind, can you remember that trigonal planar, whoa, I don't know what that is, has like a peace sign kind of shape, or Mercedes sign. And so that would make it not lopsided, and this would be non-polar. So you do have to draw the Lewis dot structure, but hopefully you can kind of think through the Lewis dot structure and just save yourself a little bit of work. So ultimately, what do we say here? No, the force cannot form because the Bf3 is non-polar, and we have to have 2 polar molecules to make that force occur. Okay. So how do I determine which one forms a stronger dipole-dipole forces? So if you're in this situation where you've got this set of 2 chemicals or this other set of 2 chemicals, how do you decide which one has the stronger force? You are going to look at their mass. You're going to look at their mass. Heavier molecules will form the stronger forces. Okay, so let me try to explain that using these pictures here. I've got 2 polar molecules right here on the left, and they're light. I've got 2 other polar molecules here on the right, and they're heavy. They're both forming dipole-dipole forces between them, but we know that the one that is heavier will be stronger. Now, we need to understand why. On the AP exam, they're going to ask you why. Okay, so here's why. It's kind of a mouthful. You ready? Do you see the positive and negative poles in this molecule? Do you imagine that they could attract to each other? I mean, this negative is attracting to this other molecule's positive, but I can imagine that it could attract to its own positive as well, right? So if this molecule is real small, then that means that these will be kind of close together, and the attraction that they have to each other is relatively great. So because they're so close to each other in a small molecule, they attract to each other in that molecule greatly, and what that does is it causes this negative to not be able to attract to the other molecule as much. So it's a strong force here actually forms a weak dipole-dipole. Let me explain it again over here with this bigger picture, see if it makes more sense. All right, this negative is attracting to this positive in the other molecule. However, we can imagine that it's probably attracting to its own positive also. So there's some attractive force here, but see how far apart they are? Because this molecule is big, that attraction right there is relatively weak. And so it doesn't affect this negative as much, and that makes the negative able to attract the other molecule with more force. It's stronger. So typically, here's what we're saying. A heavier molecule must be bigger. A bigger molecule must be able to form stronger dipole-dipole forces. So let me go to the board to show you my lovely signs here. We're now talking about dipole-dipole forces. Those form between 2 polar compounds. They both got to be polar. How do we tell which one is stronger if you're comparing 2 separate dipole-dipole forces? Look at their masses. Heavier is stronger. So I have 2 examples here. 18 grams per mole versus 2 grams per mole. Heavier is always stronger. Okay, now, when we say it's stronger, we're actually using like elementary words. We want to use college words. So the word that you're going to use is more polarizable. So instead of saying the heavier one is stronger, we say that the more polarizable, or bigger, right? We're able to polarize the molecule more, or separate those positives and negatives more, and that's why it's stronger. So we just want to kind of use those words there. Okay, I've got one more thing here. That's what the word more polarizable is here for, right? But one more thing. Do you remember yesterday we talked about isomers? And that's two different chemicals, but they have the same formula, and that would mean that they have the same mass. So how are you supposed to compare their dipole-dipole forces in that case? So in that case, you would actually look at the length of the structure itself. Usually in those situations, you're dealing with a bunch of atoms that are in a long line or in a long chain. And the longer the chain, the bigger the molecule, the more polarizable it is. So even if they have the same molar masses, look at the actual length of the molecule. If it's longer, it's like it has a heavier mass. Okay, so we're going to look at just a couple of practice problems now. If I give you all four of these gases, could you tell me which one is more polarizable? There are names there, I know it's hard to see. Methane, ethane, propane, butane. How about butane all the way on the bottom, right? So how can I tell? Well, it has the heaviest molar mass, but it also, look at this, has the longest chain, which is another way of thinking about molar mass, right? So the one that is more polarizable is the one that is heaviest or has the longest chain, and that's butane in this case. Oh, chemistry is so easy. It is. Okay, I'm going to warn you right now. People confuse ion dipoles with dipole-dipoles. Here's the confusion that happens. We said a smaller ion can get closer, and therefore it would create a stronger ion-dipole force. But when you're talking about dipole-dipoles, it's the larger molecule that is heavier that creates the stronger force. You see how people kind of get those confused? Small ion or heavy, large molecule, those things will both create strong forces. So try not to get those confused. Here's a problem for you. This would be like a test question. Imagine iodine monochloride and carbon monoxide, and they are in separate containers. Which sample contains stronger intermolecular forces? Pictures help me, so I'm going to see if this helps you. I have two separate containers. In this container, I have iodine monochloride. There it is. And when I say I have it in this container, I have like millions of iodine monochloride molecules in there, not just one. Now, here's my other sample, carbon monoxide, and I have a bunch of those. So imagine that the negative dipole and the positive dipole of two different molecules are attracting, right? Negative dipole, positive dipole of two molecules are attracting. Which one has the stronger force? How am I supposed to figure that out? Look at their masses, but how did you know to look at their masses? You first have to decide which force we're dealing with, right? Are these ion dipoles or are these dipole dipoles? Well, there's no metals. So we know there's no ionic compound formed. So it has to be that there's dipole dipoles in here. Now that you know it's dipole dipoles, you use mass. Can you tell me which one has the heavier mass? This one? And so it has the stronger forces? Awesome. Yep. So we're going to say the heavier mass is the stronger forces, and that would be ICl. And I'm just giving you an illustration here to show you why. Smaller mass means smaller molecule, and their dipoles within a single molecule actually interfere with each other. Ah, a pill got it that time. So tricky. So I will put 2 tickets in. Did I put one in for you already, Pratush? You didn't see me do that. I probably forgot. Try this practice problem while I get a ticket for you guys. I'm putting tickets in there. Anybody got an answer for me? No. What do you think? ASH3 is stronger, why? Because it's heavier. Okay, so the first thing that you have to do is think about those Lewis dot structures, right? So imagine your P, and it's connected to 3 H's, or you could think about the arsenic connected to 3 H's. When you're thinking about this though, is it possible that there's a double bond in any of these locations? No, because H can only be connected to one line, right? So is it possible that I only have those 3 lines and nothing else on P? It has to be that there's a lone pair on the P, has to be. So without doing too much work, I figured out that this is polar. Do you remember that any shape that has lone pairs on that central atom is automatically going to be polar? The one exception to that is square planar. For square planar, that's not the case, but for every other one, as soon as you see those lone pairs, it's polar, definitely. Now, what if the lone pairs weren't there? It could still be polar, so then you have to think it through. But if there's lone pairs there, it's automatically polar. Okay, so my point is, you have to go through that thinking to know that there's dipole-dipole forces involved first. You have to figure out which forces involved. Don't just go straight to mass, okay? And then once you know that this is the force involved, then you can go to mass. And then we're coming up with the answer you guys mentioned. Oh my gosh. I'm in the wrong place here, sorry. Wow, I'm in the really wrong place now. Oh, too full. Okay, so you're right, ASH3. Just want to make sure I have my correct answers on here. Okay, so one last little detail here. Dipole-dipole forces help us to understand why 2 things mix. So if you remember the other day, I was showing you water and red food coloring, and we said that those mix because they're both polar. Now you can understand that if they're both polar, they're going to form dipole-dipole forces, and that's what draws them together. If one is nonpolar, then they wouldn't be able to form the dipole-dipole forces, and that's why they're not going to mix. That's why oil doesn't mix with water. Okay, so if that makes sense to you, we're just going to do a little practice here, and we're going to end with this. On Schoology, on that exact same assignment, if you open it back up, I want you to color in the dipole-dipole forces this time. You've already colored in the rectangle on the outside, so just look at those inner squares and color in the dipole-dipoles. If you do it right, you will reveal an image. And I can give you about 5 minutes, and then I'm going to have to reveal answers. So 5 minutes, try this. Oh no. I didn't realize we were out of time. Boom. Sorry guys, I guess I'll give you the answers to that first thing tomorrow. I thought I was ringing at 1:02. I don't know where my brain went. Oh, did they change it?
Yeah.
That's what got me.